Hi everyone. Today's video is about Section 4.7 in our text, which is about optimization. In this section, the problems involve finding the maximum or minimum values of a certain quantity. And just like we did in related rates problems earlier, there is a strategy that we'll want to follow when solving these problems. The first thing we'll want to do, just like we did in related rates problems, is to draw a picture of the situation and to assign variables to quantities that are of interest to us. And then, importantly, we'll want to identify the quantity that's to be optimized, that is, the quantity we want to find a maximum for or a minimum for, and we'll want to write an equation for that quantity. Now, it'll be important for us to get whatever equation we have in terms of one single variable, because that's the situation that we know something about in this class. We know how to take derivatives, for instance, of functions of one variable. Speaking of derivatives, we know how to, given a function, how to find a derivative, find points of interest, and then use those to locate maximums and minimums. And we'll do that here in this section once we find the correct function to differentiate. And then finally, at the end of the day, we want to make sure that we answer the question that is posed to us instead of just merely computing a derivative or a number or something without putting it into context. Well, away we go with examples. In our first example, we have a rectangle, and we're told its perimeter is 100 meters. And we're to find among all such rectangles the dimensions of the one whose area is largest. Since this problem involves a rectangle, we might as well draw a rectangle, say something like this. And we'll be interested in the sides of this rectangle. Why don't we label them X and Y? And the thing that we know about this rectangle is that its perimeter has to be 100 meters. And that means that if we take 2x plus 2y, which is the perimeter of the figure, we should wind up with 100. And this, if we divide by 2, tells us that x plus y is equal to 50. Now, the thing that we're attempting to maximize here is area. And if we take the area of this rectangle, so the area is just the product of the dimensions, right? It's just x times y. Now, you might remember back from the strategy that whatever quantity it is that we want to maximize or minimize, that quantity needs to be expressed in terms of one variable. And here we've got area, a simple formula for area here, but it's still being expressed in terms of two variables, and we need to fix that. One way you can do that is go back and look at what we know here. We know that x plus y equals 50, and that tells us that y is 50 minus x. And therefore we can make this substitution. We can replace y by 50 minus x. And we can go even further with this and write this as 50x minus x squared. And now we have ourselves a function which we'll call a of x, expressed in terms of one variable, that tells us the thing that we want to maximize. Now, it'll be important for us to keep in mind which values of x are allowable. And we might think about the possibility. Well, we want to make sure that x is bigger than 0, because otherwise we don't have a rectangle. And likewise, we want y to be bigger than 0. Now we think about how big x might be. Well, suppose x is pretty big and y is pretty small. Well, the perimeter is 100. So that means that x really can't be any bigger than 50. And so we're looking at values of x that are between 0 and 50. Okay, now we have our function to maximize, and we know the interval on which we want to consider it. And that really is the hardest part of this problem, and in fact of any of the problems that we're going to deal with. So the next thing that we'll want to do is maximize this, and we do this. The first step to doing that is to look at the derivative of the function. So a prime of x is 50 minus 2x. And we'll be interested in where that, derivative is either 0 or undefined. And we see that the derivative is never undefined. However, if we set the derivative equal to 0, then that says that x must be equal to 25. And then the question is, well, does x equal 25 correspond to a minimum for this function? And one way we can sort of tell that is to make a little sign chart. In fact, maybe we'll do this next slide. So here we have a blank slide. And remember, our a of x was 50x minus x squared, and our a prime of x was 50 minus 2x. And we saw that x equaling 25 was a point of interest. Well, we can look here at a sign chart, put x equals 25 there, and if we look at the sign of f prime, or excuse me, in this case it's a prime, right? Well, if x is bigger than 25, then the derivative, you can pick a test value, like if x is 30, the derivative is going to be negative there. Whereas if x is smaller than 25, say x is 20, then the derivative will be positive there. And so what we wind up with is that the function a increases to the left of 25 and decreases to the right. So we have a max there at x equals 25. And now finally we want to answer the question. The question asks for the dimensions of the rectangle that maximizes the area. And so we might want to try and write down something like the dimensions are x equals 25. And now we also remember that we have a value of y that we need to get. And remember, y was 50 minus x. So that means that y is 25 as well. And so this rectangle that maximizes area with a fixed perimeter is a square, which is something that we might have guessed from the outset. Our next example bears some similarity to the last example we did. This time, instead of having a rectangle to contend with, we have a box to contend with. We have a box, it's got a square base and an open top, meaning it's just got the bottom and the sides. And there are 1,200 square centimeters of material available to make this box. And among these boxes, we want to find the largest possible volume of the box. Now, how do we get started on this? Well, just like on the previous problem, we want to create a picture, and this time we've got our make a picture of a box with a square base. So it looks something like this. And remember that the base is a square. We'll let the dimensions of the base be x, and then there's the height of the box to take into account, which would be y. Now, what do we know about this box? We know that there are 1,200 square centimeters of material available, which means that the area of the base, together with the area of the sides, has to be, well, we'll set it equal to 1,200. And so the area of the base is x squared. Now the area of each side is x times y, and there are 4 sides, so that's 4 times xy. And we're going to go ahead and use the maximum amount of material. And anticipating that we're going to need to eliminate one of the variables, if we solve for y in this equation, we wind up with 1,200 minus x squared over 4x. All right. Well, we'll just keep that in our hip pocket for a while and hope that we can use it a little bit later. Meanwhile, we know that if we want the volume of a box like this, or the volume contained in the box, that we want to multiply all the dimensions together. That means we take x times x, which is x squared, and then we multiply by y. Now, as in the previous example, we have this quantity now that we wish to maximize, but it is expressed in terms of more than one variable, and therefore we need to eliminate one of the variables. And it just so happens that we conveniently have y expressed in terms of x, and we can just go ahead and use that. So this is x squared times this whole mess, 1,200, minus x squared all over 4x. And that becomes, after simplification, that becomes what? Well, it becomes 300x minus x cubed over 4. And just as in the previous example, we want to think a little bit about the values of x that are going to make sense here. Now, x is going to need to be bigger than 0, but how big could it possibly be? Well, imagine if x were big and y were small, then the material used would essentially be x squared. And that means that x squared, it can't be any more than 1,200. So that means that x has got to be less than the root of 1,200. So whatever value, if we come up using the derivative with some number that's going to maximize this volume, we'll want to at least check that it lives within this interval, 0 to the root of 1,200. Okay, now we're going to give this function a name just like we did the last time. This time we're going to call it v of x, not v prime of x, but v of x. All right, once we have that, that's the hardest part, and now it's just the mechanics of creating the derivative and finding the points of interest. Well, let's compute the derivative. It's v prime of x. and that's 300 minus 3x squared over 4. And if we then set v prime of x equal to 0 and solve this equation, right, we would have 300 minus 3x squared over 4 equaling 0. If we solve for x in that equation, that gives us x equals 20. Now you might notice that 20 does actually live within this interval from 0 to the root of 1200, so that's very good. And the question then is there really a maximum there? And we could, just like we did in the last example, produce a sign chart and use the first derivatives test to tell us that there is indeed a maximum there. However, in this example, I want to illustrate a method that we really hadn't talked about before in class, and that's something called the second derivatives test. Now, here's the situation. If you take the second derivative of v, you wind up with this function minus 3 halves x. And that turns out to be less than 0 when x is equal to 20, which is our special value of x. Okay, so if we plug in x equals 20, we get a number less than 0. Now the second derivatives test tells us that if you have a special number like 20 where the derivative is either 0, and you then look at the second derivative, if the second derivative is negative, then you know that you have a maximum at x equals 20. If the second derivative is positive, then you know you have a minimum at x equals 20. So here, because the second derivative is negative when x equals 20, we get a max at x equals 20. It's the second derivatives test. If you want to look that up in the book, it's in section 4.3. Now remember, we don't have to use the second derivatives test here. We could do a sign chart just like we did in the first example and come up with the exact same result. Now, we need to make sure that we answer the question, right? And the question was, we wanted to produce a, or find the volume, actually, of the box, that gives the maximum volume. So let's see if we can compute that, right? So the max volume is going to be, well, what was volume anyway? It was x squared times y. Now remember, our value of x is 20, so that's going to be 20 squared. And then we have to figure out what y is. Now remember that y was 1200 minus x squared. Over 4x. So let's see if we can figure out what that is. Well, in this case, x is 20. 20 squared is 400. 1200 minus 400 is 800. So let's write that down. And then x was 20. 4 times 20 is 80. So that means that y should be 10, right? So now up here, I want to make sure I put a 10 for my y. Okay. And what do we get? Well, we get 20 squared times 10, which turns out to be 4,000. And I think the units are going to be cubic centimeters. And that's the end of that example. Here, our next example shows us that things don't always turn out quite as nicely as they did in the first two examples. Here we have the sine curve, and we want to find the point on that curve that's closest to this given point, 4, 2. And we might begin this whole process by drawing a picture of the sine curve, or at least one cycle of it, up to 2 pi here. Now the point 4, 2 would probably be sitting up around here somewhere. So let's write it. And we're looking for this special point on the sine curve that where if we draw the line from that point to the point 4, 2, that the length of that line segment is as short as it can be. Now that point on the sine curve has the form x, comma, sine of x. And we just now want to minimize the distance between x, comma, sine x and 4, 2. And we have to remember what that distance d is. Well, we have this thing called the distance formula. And it tells us that to find the distance between 2 points, we take the square root of first the square of the difference between the first 2 coordinates and the square of the difference between the last 2 coordinates. And just like in the previous example, we might want to think about the values of x for which this makes sense. Now, it's probably pretty clear that we want x to be between 0 and 2 pi, or maybe even between 0 and pi. But really, there's no physical reason why we can't let x be any real number. And so we'll just let x be anything that we want it to be. Now, the square root complicates things when we take derivatives, so it's equivalent or just as good for us to minimize the square of this little d. And if we do that, we get x minus 4 squared plus sine x minus 2 squared on the same interval. A value of x that makes capital D as small as possible will also make little d as small as possible. And it's defined on this same interval. And, well, the next step, of course, in this whole process is to examine the derivative. So if we look at d prime, well, what do we get when we take d prime? Well, we get 2 times x minus 4. That's the derivative of the first bit. And then for the second bit, well, we bring down the 2, we leave the inside alone. And then we multiply by the derivative of the inside, which is cosine of x. And then, what do you want to do? Well, this derivative is defined everywhere, so what you do is now just check to see where it's equal to 0. And then you get this equation. You can imagine setting this, this big long mess of stuff equal to 0. And if you do that, you'll wind up with this equation that is impossible to solve in closed form for x. Right? In fact, we talked a little bit about situations like this way back in Chapter 2 when we discussed the intermediate value theorem, where, you know, sometimes you've got these equations that you want to solve and you just can't isolate the variable that you want to isolate. So here, what we might want to do is just try to find an approximate solution. So you could graph d prime of x. Oh. So we're going to find an approximate value of x by graphing d prime of x. And you could maybe do this on your calculator or on Mathematica or something like that. And if you do that, if this is like 2 and this is 3, you'll get a picture that looks, I don't know, a little something like this. Okay, so that's y equals d prime of x. And what you're interested in is where d prime of x equals 0. That is this spot right there. So d prime of x equals 0 implies from the graph that you get that x is about 2.65. Okay, and we can see something from this graph of d prime. For instance, that d prime is negative here to the left of 2.65, and it's positive to the right, which means that the original function, capital D, is decreasing and then increasing, and so we know that we have a minimum here at x equals 2.65. And now remember, the original question asked us to find the point that's closest to 4, 2. And so the point that we want, that the problem asks us to determine, is 2.65, or at least it's approximately 2.65, comma the sine of 2.65. And that is the end of that example. Our last example is an area problem that brings us sort of full circle back to the first example, where we also considered an area problem. Here we have a poster with some margins. Top and bottom margins are 6 centimeters, and then we have these side margins which are declared to be 4 centimeters. Inside the margins we have a printed area which is fixed at 384 square centimeters, and we're supposed to find the dimensions overall of the poster with the smallest area. So a picture of this might look something like this. So we have this printed material inside. That's our printed material. But around the edges of this printed material we have some margins. So we have 6-inch or 6 centimeter margins, I guess, on the top and bottom. And then on the sides we have somewhat smaller margins, 4 centimeter margins on the sides. And so what we really have is a poster that's frame or outer frame looks something like this. And what we're asked to do, given that this is 6 and 6, and that's 4 and 4, and that, and also given that the inner printed region is fixed to be 384 square centimeters, we want to find the overall, the dimensions of the poster with the overall smallest area. So what I decided to do in this problem is to label that side X and this side Y. And then what do we know about this situation? Well, if we take Y and we subtract off the 4-inch margins on either side, we get a Y minus 8. And then for X, if we subtract off the 6-inch margins on either side of the printed area, we get x minus 12. And if I multiply those two things together, that is exactly the area of the printed region. That is the 384. Right? Now, if you go ahead and mess around with that equation, you can solve for y in this. And if you do that, you'll get y is 384 over x minus 12 plus 8. Okay. Now, remember that we are to find the dimensions of the overall poster with the smallest area. So the area of the overall poster, including the area that's not printed, is just x times y, just like it was in our first example. But now we again realize that we have this equation and we've got too many variables. But remember, we already solved for y in terms of x. So A is, the area is x times 384 over x minus 12 plus 8. And if you go ahead and multiply that out, well, actually, first, before we multiply this out, let's just sort of provisionally put an interval on which we want to sort of mess around with this thing. So we see, for instance, that it's undefined at x equals 12. Right, I mean, x is at least 12, right, because we've got 6-inch margins on either side of the printed region. So maybe we just think about x as being anything bigger than 12. Now let's do one more step of simplification here. If we multiply through by x, we get 384x over x minus 12 plus 8x. So that's our function, a of x. Again, defined on the interval from 12 to infinity. Now, as in all of these problems, once you're at this step, that's sort of the hardest step, is getting to here. And now we need to take the derivative and see where it's equal to 0 or where it's undefined. Now, go on to the next slide, and we take the derivative. Using the quotient rule, we get that a prime of x, right, so that's a prime of x, not a double prime, but a prime of x, turns out to be 384 times x minus 12 minus 384x over x minus 12 squared plus 8. That's the derivative, and you might want to take a moment now and just make sure that that has been computed correctly. Now, if you set a prime of x equal to 0 and you solve for x, you're going to get a mess of algebra to do. However, it does just in the end yield a quadratic equation, and you should be able to go and solve that quadratic equation and wind up with x being equal to 36. Now you might remember that that x minus 12 times y minus 8 has to be 384. So that tells us, together with x equals 36, that y must be 24. And if you want to know that x equals 36 does indeed give rise to a minimum, you could apply either the first or the second derivatives test, although both of those would be rather unpleasant to implement in this particular example. But anyway, these dimensions, x equals 36 and y equals 24, are the desired dimensions. And that's the end.